Hello, everyone, and welcome to the next lesson in our Cosmic Adventure lecture series. My name is Dr. Valerie Rapson. I'm an assistant professor of physics and astronomy at SUNY Oneonta and a past director of the Dudley Observatory. Today's lesson is going to focus on gravitational waves. Now, I remember the first time I gave a public lesson on gravitational waves, it was back probably mid to late 2016. And that was shortly after the first official detection of gravitational waves. And at that time, only a handful of discoveries have been made. But now we have detected almost 100 official detections. So I thought it was time to update you all on what we found over the last few years. So today what we'll do is we'll start with a basic introduction to gravitational waves, talk about what they are, how they're created, and what their properties are. Then we'll take a look at how we actually detect them using specialized observatories on Earth, and then we'll wrap up with some of the most exciting discoveries to date. So by the end of this lesson, you will all be up to date on all of the cool things we've discovered in the world of gravitational wave astronomy. Before we can even get into the details of gravitational waves, we really have to take a step back and kind of get our minds in the same realm as Einstein. Now, I know that's a bit intimidating, right? Einstein's one of the most famous physicists. He came up with the theory of special and general relativity, but we don't need to know everything about those theories to have a basic understanding of gravitational waves. But one thing we do need to understand is Einstein's idea of four-dimensional spacetime. If four-dimensional space-time did not exist, then gravitational waves would not be possible as we understand them today. So here's what we need to know. Einstein proposed that we lived in, or we do live in a four-dimensional space-time. That's the three dimensions that we're familiar with. So I can move left, right, up, down, forwards, and backwards. But we also add the fourth dimension of time to that, and we link it all together. This means that when I move through space, time also has to move forward with me. And if you manipulate time or space, you are also manipulating the other dimensions all at the same time. So basically, time and space are all interconnected. Now, the best way to think about our four-dimensional space-time is to imagine it like a rubber sheet. And you can see that here in the little cartoon. Basically, the fabric of space-time is represented by this grid pattern here. And if we have massive objects like stars or planets or galaxies that are sitting in space-time, then they can actually bend space-time. So if you were to place a heavy object on a rubber sheet, it would bend. The same type of thing is happening in our four-dimensional space-time. So in the cartoon, you might have a more massive object like a star. You can see that bends space-time more. And less massive objects like planets or maybe moons, they would be bending space-time a bit less. Now, it's pretty hard to depict a four-dimensional object on a two-dimensional screen. So I like this little animation here that shows what it looks like in space-time as an object orbits and how it warps space-time. So anytime an object, a massive object, moves through space-time, it drags space-time along with it. So if you imagine that 3D cube there with that white circle, maybe as a star or a planet moving through space-time, you can see that as it goes in that circle, it is bending, dragging, and warping space-time with it. This is ultimately what creates the force of gravity. Turns out gravity isn't an actual force after all, but just the curvature and bending of space-time that basically produces what we feel as the force of gravity. So with this basic setup and understanding of 4D space-time, we can now take a look at what gravitational waves are and how they move through this 4D space-time. So gravitational waves, they're just ripples through this four-dimensional space-time. You can see in the little animation in the bottom, we have two massive objects that are orbiting around each other. And as they orbit around each other, they're producing gravitational waves. Technically, anytime you have an object that is accelerating, that means the object could be spinning, orbiting, it could be exploding. As long as it's moving with some sort of acceleration and it's doing so in a slightly non-symmetric way, you will produce gravitational waves. You will produce these ripples through space-time. If everything is perfectly symmetric or spherical, then Einstein's equations tell us that gravitational waves will not be produced. But in our cartoon example here, you can see that we have two objects. They appear to be slightly different masses. If we imagine them orbiting one another and potentially spiraling in towards one another, that means they're accelerating and they're producing those ripples through space-time. So gravitational waves in the simplest way can be thought of like waves on a pond, right? We just see the waves, they travel outward, they move outward from the central source that generated them. And ultimately, we can detect these gravitational waves, these ripples, here on planet Earth. Now, gravitational waves were discovered not too long ago, but they were actually predicted by Einstein's theory of general relativity. So all of the mathematics that Einstein worked through in the early 1900s, he predicted that gravitational waves should be emitted by these non-symmetric moving objects. Took us just about 100 years to actually detect it though and prove that he was actually right. But all of general relativity predicts that this should happen, and we now know that that indeed is the case. So with a basic understanding of what gravitational waves are, we can now ask ourselves, well, what types of objects are we going to see commonly producing gravitational waves? Well, we know just about any non-symmetric orbiting or moving object will create gravitational waves. So a simple planet orbiting the sun is going to produce a small amount of gravitational waves. And indeed, the Earth orbiting the sun does that. We also can have more dramatic things that produce gravitational waves. These could be things like supernova explosions. You can see a picture of a supernova remnant on the left-hand side here. So this is just a massive star that has died and exploded. And as long as it does it in a slightly asymmetric way, that explosion and the accelerating material will generate a burst of gravitational waves. We also have neutron stars or pulsars or black holes. If they happen to be spinning or orbiting each other, they can produce gravitational waves. So in the middle here, you can see this is a real image of the pulsar in the center of the Crab Nebula. That's just the core of the leftover star after a supernova explosion. It is spinning, rotating very quickly, sending beams of radio light in our direction. And pulsars that are just spinning like that, they will produce gravitational waves. And especially if you have two objects, whether they're neutron star, pulsar, black hole, if they're orbiting one another and spiraling towards one another, they're going to lose some energy. And as their orbit decays, they will also produce gravitational waves. So that cartoon over here on the right-hand side, that's showing a binary black hole system and what the warped space-time around it might look like as they orbit around and produce their gravitational waves. So there are many different types of things that can make gravitational waves, but these are the most common, and these are some of the ones that we have the ability to detect with our current technology. We're maybe not quite at some of the lower end of detecting planets orbiting stars and the gravitational waves that they produce. But any of these other bursts of gravitational waves, and especially the orbiting objects that are decaying in their orbits, those are things that we are able to currently detect as of today. So with a basic understanding of gravitational waves and how they're produced, we can now look at the specific properties of gravitational waves. All of these properties are predicted by general relativity, and these properties have been confirmed by all of our detections here on Earth. So let's look at some more information about gravitational waves. First thing to note about them is that they are invisible. And by invisible, what I mean is that they are not waves like light waves. They're not, emitting any energy that is visible to our eyes or to a standard telescope. And we also don't physically see space-time shaking or moving. The gravitational wave signal, these ripples, are very low level. They are very microscopic, and we don't physically see them. So we are just detecting basically a stretching and squeezing of space-time. These ripples are expanding and stretching and squeezing space-time, and you'll see in a moment exactly how we're able to detect that, but we don't physically see them, at least not in the standard way that we see other objects in outer space. These gravitational waves, they also travel unimpeded by matter. So you can have a binary neutron star system like the animation on the right there producing gravitational waves. It could be, billions of light years away, and those waves will travel through space, through any material that they encounter, and still make it to Earth unimpeded. The waves also travel at the speed of light. That was a prediction of Einstein's general relativity, and that turns out to be true. We can also take a look at the strength and the structure of the gravitational waves. We know that the amplitude or the strength of the gravitational wave decreases with distance, kind of in the same way that light does. As light travels, it spreads out into outer space. That means that over a current surface area or a current point in space, you're going to receive less light the further away you are from an object. And the gravitational waves seem to spread out and decay in the same way that light does. The initial amplitude or the strength of the gravitational wave is dependent on the acceleration of the object that created it. So faster orbiting objects or a stronger explosion would create a stronger initial gravitational wave signal. Gravitational waves, they also experience redshift. That is basically the stretching of space-time, and they exactly how we detect them can be shifted. So this is the same thing that happens to light as it travels long distances in outer space. And finally, the gravitational waves, they carry away energy from the system. That allows objects to decay as they orbit. As they get closer, they will release some energy in the form of gravitational waves, and that will help them in spiral towards one another and often ultimately combine into one singular object. So that's just kind of a basic summary of some of the properties of gravitational waves. And now we can take a look at some of our first inklings into whether or not these gravitational waves actually exist. Einstein's theory in math says they do, but until we actually observe them in outer space, we won't know for sure if his mathematical calculations are correct. So the very first indirect detection of a gravitational wave came in 1974. There were two scientists, Hulse and Taylor. They were observing a pulsar neutron star system orbiting around one another. So if you take a look at the cartoon on the left here, you have a pulsar and a neutron star. These are both the same type of object. They are the cores of massive stars that have died and exploded. Neutron stars are just a ball of neutrons that result from that stellar evolution. Pulsars are the same thing. They're just rapidly rotating neutron stars, and they happen to beam radio signals out both ends, and we're able to detect those on Earth. So this binary pulsar neutron star system was detected, and what Hulse and Taylor did is they monitored the orbital period over time. And you can see the actual data on the right-hand side. This system was tracked from 1974 in this graph all the way up to 2005. All of the black data points are showing a measurement of the system here. And what you see is that the black data points, they trend downward as time goes by. This downward trend, what it means is that the orbital rate of the pulsar neutron star system is shrinking, and it's taking less time for the objects to orbit around one another. So this axis here can be thought of basically as how quickly the objects are orbiting one another, and it's a way of measuring how they are in spiraling and how close to one another they are in outer space. So you can see that downward trend, meaning that the objects are spiraling around one another and getting closer and closer and closer as the years go by. And you can take those data points and you can also put on the same plot the general relativity prediction, assuming that gravitational waves are being emitted by the system, they are carrying away some of the energy, and they are responsible in part for these two objects in spiraling and having that decaying orbit. So on this chart too, the solid line, which appears to directly connect pretty much all the data points, that is the general relativity prediction, assuming gravitational waves exist. And you can see that, again, it definitely seems to connect most of the data points. It fits the data essentially exactly. So what that means is while we didn't at the time have, an instrument to actually detect or measure the gravitational waves, we could infer that they existed because the motions of these two objects told us that they must exist. Their motion matched exactly what general relativity predicted, assuming gravitational waves were being emitted. So this was back in 1974. The astronomers were pretty sure that gravitational waves existed. But they did have to wait a great deal of time. They did have to wait about 35 years for the official first detection of a gravitational wave. The first signal was detected in 2015, and it was officially announced and released in February of 2016. And that detection came almost exactly 100 years after Einstein first published general relativity and predicted that gravitational waves existed. So all of this was the perfect culmination of Einstein's work, and it really proved once again that general relativity was indeed the best way to describe objects in our universe. So now that we know that gravitational waves exist, let's look at exactly how we detect them and how that 2015 discovery was actually made. Here's a nice little map that shows all of the current and planned gravitational wave observatories. The ones that you might be familiar with are the two LIGO observatories that are here in the United States. Virgo is also a common observatory. That one is over in Italy. It's been operational for a few years now, or actually, I think it's been operational for as long as LIGO has been operational, but it only recently was upgraded to the point where it was particularly useful to work in tandem with the LIGO facilities. There is also a facility up in Germany, the GEO 600 facility. CAGRA, this is over in Japan. This is the first underground gravitational wave observatory. It went online in 2020. And there is a planned observatory called LIGO India, which is going to be located in India. So each of these observatories are capable of detecting gravitational waves, and they continuously go through upgrades as technology improves and our ability to detect gravitational waves improves. We want to make sure that we're able to detect fainter and fainter signals. So these systems are often taken offline, upgraded, and restarted. So with gravitational waves nowadays, you often see kind of a burst of detections where they will detect a bunch of waves, they will do some press releases, then some of the systems will go offline for upgrades, then they'll be able to be more sensitive and detect even more gravitational waves as time goes by. So we have a whole bunch of observatories located across the world, and let's take a look at exactly how they work. What does a gravitational wave observatory actually look like, and how does it detect the stretching and squeezing of space-time? So here is LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. There's two of them, one in Washington and one in Louisiana. And basically what they are two 2-mile long tubes. There is a laser system in the main building that shoots lasers down both of these tubes. There's a mirror at the end of the system which bounces the signal back. And back here where the laser originated is where the system can detect any gravitational waves. And on the next slide, you'll see some pictures and animations of exactly how these detections work. But I just want to kind of show you what the system looks like here at a 90-degree angle and mention that the way our systems work with the current technology is that they're capable of detecting signals from more massive objects and really large explosions. And primarily what we get are detections from orbiting and merging objects. So when we get into talking about the different gravitational wave detections, you'll see that most of them are binary black holes or binary neutron star mergers, because that's what our system is currently sensitive to. As we continue to upgrade these and other systems, we'll be able to detect fainter and fainter gravitational wave signals that come from some of the other objects that we had mentioned a few minutes ago. So with LIGO and all of the gravitational wave observatories, how do we actually detect a gravitational wave signal? Well, here's what the inside of the facility looks like. Here on the left, you can see a laser source. That would be in the main white building that we showed. And the laser shoots forward and passes through a beam splitter. The beam splitter's job is to split the laser beam, send the same laser beam, the same initial signal, down those two long arms. So the beam splitter sends a signal down one arm and also down the second arm at the same time. There is a very delicately suspended mirror at both ends. The mirror then reflects the laser signal directly back to the beam splitter, and the beam splitter then combines the signal, sends it out to a detecting device, and that is officially where the laser signal is remeasured. So in this system, we're not, gathering gravitational wave energy or anything like that. We're actually using lasers to determine whether or not a gravitational wave passed through Earth at any moment in time. That's the basic idea. So with this system, what it's designed to do and exactly how the mirrors are hung and the length of the arms, the system is designed so that actually we don't detect anything. We're not supposed to detect a laser signal. So the laser goes down, split into the two arms, it bounces back, and the system is designed such that the length that the laser travels brings the laser back together, and the two waves are exactly out of phase. That means that the peaks of one waves match with the troughs of the second waves. And when you add those two waves together, the peak cancels out the trough, and you essentially get zero signal. So if everything is still, if there are no gravitational waves passing by Earth, then you won't detect anything. You won't see anything on the light detecting device. But if a gravitational wave signal does pass by, that's going to stretch and squeeze space-time. It's literally going to jiggle the mirrors a little bit. And when the light is recombined, it's not going to be exactly out of phase anymore. It'll be partly in phase, and we will see a signal in that light detector. So here's a little animation of what's happening. Again, laser, beam splitter, down the two arms, hitting the mirrors, the light comes back and it goes to the detector. And we're going to repeat the little video here, but it just shows that initially the light gets combined, it cancels out, there is no signal detected. But if anything shakes those mirrors or stretches and squeezes space-time, basically changing the distance that the laser beam has to travel, then we will ultimately see a signal. So that's how we do it. We use lasers. We use them to detect if space-time on Earth is stretching or squeezing at all, wiggling our mirrors, and causing the lasers to combine a little bit more in phase as opposed to out of phase. Now, one more quick thing. This picture makes it look awfully dramatic, but the stretching and squeezing of space-time that we see is incredibly small. We're looking for mirror movement and space-time manipulation on scales 1/1000th the size of a proton. So very, very much microscopic subatomic scales. That is what we are sensitive to with LIGO and many of these other gravitational wave observatories. So really detecting gravitational wave signals in the first place is a pretty amazing feat. All right, so now that we know what gravitational waves are and exactly how we detect them, let's take a look at what a signal actually looks like. You're going to see a couple of graphs like this and some simulations and videos later on. And we're also going to talk about the properties of the objects that are creating the gravitational waves. And I wanted to take a moment and just briefly explain to you how we know things like the strength of the gravitational wave or the size of the object or the spin rate of the object. All of these properties can be teased out from the gravitational wave signal. So I wanted to give you a heads up on what the signals look like and talk about how we know these things so that when I tell you it's a 30 mass solar mass black hole, you can trust me and know that the scientists analyzed the data and get a little bit of an idea of how they figured it out. So here we have a chart showing a gravitational wave signal. We have time on the x-axis, so this is basically us monitoring things in time. And the y-axis is the strength, the amplitude of the gravitational wave signal. And these numbers are multiplied by 10 to the minus 20. So remember, they're very, very small. Basically, what you see are waves here. These waves are the gravitational wave signal. Again, we're actually detecting the changes in the laser light, and then we are converting it to a depiction of what the gravitational wave is doing. And as time progresses, you can see that the height of the signal changes, the frequency or how close together the peaks and troughs are changes, ultimately reaching a maximum on the right in only about 0.1 seconds. So these signals that come by Earth, they don't last very long. Remember, they're flying by at the speed of light, and we don't detect them for very long. So when we have a signal that looks like this is an example of a very simple, two objects orbiting and inspiraling towards one another. And properties that we can look at here, as we said, are things like frequency and amplitude. The frequency, how quickly the gravitational wave is moving, that gives us a sense of the rotational and orbital speed. So objects that are orbiting one another faster, they're going to create a more frequent gravitational wave signal until they ultimately combine, and then they will stop producing gravitational waves. So by looking at the frequency on this graph, we can figure out rotational or orbital speed. Amplitude is also the strength of the signal, so we can get a sense of how powerful the emission was, and exactly a little bit more about how massive the objects were that created the gravitational wave signal. We also can look at the duration, so how long did the signal last? So in this case, it was only 0.1 seconds, but the duration, as well as the final frequency, what is the peak or the trough down here, that gives us a sense of the rotation rate of the individual objects. So not the orbital rate of the two objects going around each other, but if you have, say, two stars orbiting one another, producing gravitational waves, they themselves are spinning on their axis, and we can actually measure their spin rate based on the duration and final frequency of the gravitational waves. Now this depiction is pretty simple. We're assuming, two objects of similar mass that maybe aren't even spinning at all. The gravitational wave looks really simple. But in a more realistic scenario, a gravitational wave signal might look something like this. So again, you've got time on the x-axis and some sort of signal strength represented on the y-axis. And you can see that the overall shape of the wave is not symmetric anymore. It's got some, weird patterns to it. And by looking at this shape, we can actually measure not just the rotation rate of the individual objects, but the axial tilt of those objects too, which is pretty amazing. So we can know exactly how a star or even a black hole is tilted along with how fast it's moving. And then if we take all of this information and put it together, so frequency, amplitude, time, final frequency, and the shape of the signal, we can model it all, put all the properties together, and ultimately get the masses of the two objects. The theory of general relativity provides us with the math to do that. So I'm not going to show you the equations or the math or anything. That would take a lot longer than I have today. But you'll have to trust me a little bit that we can actually look at these signals, we can look at the different properties and tease out some of the individual properties of the actual objects creating the signal, which is, I think, a really, really amazing feat as well. All right, so we've covered the basics. Let's take a look at some of the actual detections, and we'll watch a few videos along the way as well that do an excellent job of showing you some simulations and talking about what actually happened, and also letting you hear some of the gravitational wave signals as well. So the very first detection, gravitational wave 150914, these numbers, by the way, are the date that the signal came in. So this was September 14th of 2015. This was the very first detection. It was a 36 and 29 solar mass black hole that were orbiting around each other. And over a short amount of time, they ended up merging together and producing the gravitational wave signals along the way. On the left, you have a simplified version of the results. On the right, you have some more of the actual data. Basically, we've got our two black holes here. They're spiraling around one another. As time progresses, they get closer and closer until they ultimately merge. And when they merge together, they create one more massive black hole. And the signal is down here. So strain represents the stretching, the signal strength. The gray line, that is a smooth version of the actual data. And the red line that overlies on top of it is general relativity's model, the prediction. And you can see that the gray and the red match exactly, which means that we did indeed detect a real gravitational wave signal. And we can go back through and, just like we just talked about, tease out things like mass and spin rate and all of that. So as the objects get closer and closer together, you can see the frequency increases, the data gets squished together until ultimately they combine. You have that maximum amplitude where they released a burst of gravitational waves, and then you get what we call a ring down, where basically the signal goes to zero. And after they're done spiraling and merging, we don't see a gravitational wave signal anymore because the object is combined. It may have stopped moving, but if it is moving, it's doing so in a symmetric way such that it often doesn't produce gravitational waves. The right-hand side are the same kinds of charts as you see on the bottom left, and they are for the three observatories that the two observatories, I should say, that have the data, and then the two sets of data are overlapped on the bottom. So the detection was made in the two LIGO observatories. There is a model kind of in the background there, a lighter yellow line, and then the actual data is the dark orange and the blue there. And you can see that the data matches very, very closely. The signal strengths and the signal frequencies are very, very similar in both detectors. So that means that we're confident that what was detected was a gravitational wave that passed through Earth, hit one detector first, and then hit the second detector a short time after. Same signal must mean that it actually is a gravitational wave detection that came from outer space. Now, since this was the first detection of a real gravitational wave signal, they did a ton of press releases. They made a bunch of simulations to show what was going on because the instrument team wanted to share their science results with the public. So in a moment, I'm going to play this video. It was put together by The Guardian, and it's just a compilation of different pieces of the original press release where the scientists talk about the discovery and how it was made. And they also let you hear the gravitational wave signal for the first time. Remember, we are detecting light of a certain frequency caused by gravitational waves that are wiggling the mirrors and generating that laser signal. And we can take the assumed frequency of the gravitational waves, shift it into the audible range, and actually listen to the signal that was produced by these two inspiraling and colliding black holes. So let me play the video, and you can enjoy listening to the black hole collision.
We have detected gravitational waves. We did it. So these gravitational waves were produced by two colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago. They were detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. As the black holes spin around each other, all right, the stars behind them are warped, and that's because the strong gravitational fields bend the light that comes around. But what I want you to pay attention to in this video is the fact that as they orbit, the black holes are getting closer and closer to one another. The orbit is speeding up, and eventually they're going to merge. The event horizons are going to join, boom. They produce one big black hole, which relaxes, and you see a little bit of vibration there, and it becomes two smaller black holes die, one bigger black hole is born. The green that you see are the gravitational waves that are produced as the black holes orbit around one another. Their orbit decays and they merge together. All right. So they're spinning around. You see they're getting closer and closer together. As they get closer and closer together, more gravitational waves, they merge, and there's this burst of gravitational waves that travels for 1.3 billion years. It passes through everything. It goes right through matter, right through stars, and it eventually gets to the Earth. All right, and when it gets to the Earth, the gravitational wave passes, and what it's going to do is stretch and compress space as these waves pass. And you'll see that the Earth is jiggling like jello. I don't want people to be scared here. The Earth doesn't really do this. This effect is greatly, greatly exaggerated, but it gives you the effect. And then we zoom in, and how we detect these are using the interferometer that's in LIGO.
We can hear gravitational waves. We can hear the universe. So what we have done is taken the real signal and shifted a bit in frequency, but it's still the real signal. Did you hear the chirp? There's a rumbling noise, and then there's a chirp. Let me do that again. Whoop. That's the chirp we've been looking for.
I really love listening to that signal because it feels so anticlimactic. Like two colliding black holes, you expect this huge bang and you get this tiny little chirp, tiny little signal, but really, really fascinating nonetheless. So that was the very first gravitational wave detection. And I want to show you one more quick thing about it before we move on to the next part. The next logical question that people ask is often, where did this signal come from? Where were these two black holes that collided? Were they in our galaxy? Were they beyond our galaxy? Well, first of all, the galaxies or the black holes were definitely outside of our galaxy. They were a little over 1 billion light years away. But it's very tricky, or at least it was very tricky at the time, to pinpoint exactly where the galaxy was and where the black holes were. So with only two detectors, the two LIGO detectors, it's tricky to triangulate. You really need 3 detectors, if not more. So the best that they could do is essentially create a swath of the sky where they would say, okay, somewhere within this region is where that black hole collision occurred. So if you look at the picture on the right-hand side, this shows our Milky Way galaxy across the center here. And this outline here in the different colors, this is the general region where that black hole pair could have been. And it's, probably originated somewhere near the center, but it really could have been anywhere along this line here. And this is a tremendous region of space, right? There's probably, 100 billion galaxies or so in this region. So we really don't know exactly where the black hole came from. But we can do our best. The way that they do this, by the way, is they look at the delay between the two detectors and also which arms have the stronger signal. And that will allow them to kind of generally get a region of sky. And the delay between signal time, it should be, whatever the speed of light is between the two detectors, that allows them to confirm that it's a gravitational wave source and also get a little sense of the angle that the light was coming in at, the gravitational waves were coming in at, and allow them to roughly give an idea of where in the sky it was. So all I can say is somewhere in the southern galactic hemisphere, along this kind of colorful region in the sky right here. But for this one, we definitely can't say exactly what galaxy the black holes came from. Now we're going to jump ahead a little bit to detection 4, gravitational wave 170814. This signal was detected not just by the 2 LIGO observatories, but by the Virgo observatory as well. And this is going to allow us to pinpoint more precisely the location of where the collision occurred. So this again was 2 black holes colliding with one another. And on the right-hand side, you can see the signal from each of the detectors. So the one on the left here, this is the Hanford, Washington signal. The one in the middle is Livingston, Louisiana. And the one on the right is the Virgo detector over in Europe. On the top, you have signal to noise. So the peak up here, this is where the strongest detection came from. The middle is kind of a color plot. So when we saw the chirp in the previous video, basically the signal kind of went to the left and up. These colored lines here, that shows the strength of the gravitational wave signal. So that's the chirp in frequency and color space there. And then the more common version of the signal that we've been looking at in graphs so far are represented on the bottom, where the actual data is the red, the blue, and the purple, and then a general relativity fit is laying on top of it as the darker line signal there. So again, each of these detectors detected the same signal, and it was all detected within the same time difference. So the gravitational wave signal literally traveled through the Earth. I believe it was detected by the LIGO observatories first, and then the Virgo observatory at the end, again at the appropriate distance for these waves to travel through the Earth at the speed of light. So we know again that these were two black holes that collided in space, producing a real gravitational wave signal. Now, since we have 3 observatories, we can triangulate where in the sky a little bit better. And the result that we get is something like this. So this picture actually shows all 4, or actually 5 gravitational wave signals up until that point. So there's 1, 2, 3 confirmed detection, a potential detection in orange here at the time, and then the gravitational wave detection that we've just been talking about, number 4, originated from somewhere within this green circle down here. So you can see that, when you only have 2 detectors, you have these huge paths on the sky, and you don't really know where the signal came from. But when you have 3 detectors, you can triangulate much better, and you can narrow it down. Again, we're still not good enough at this point with these 3 detectors with this particular signal to say, it's exactly this galaxy, I can see it, I know where it came from, but the region is much, much more narrow, and they could look for, other things that might suggest a gravitational wave and a binary black hole collided in that region using other types of observatories on Earth. So the more data we get and the more observatories that come online, the better we get at detecting gravitational waves, and the better we can triangulate and say exactly where they came from. Moving on now to detection number 5. This one was really cool because it was the first binary neutron star merger where we detected gravitational waves. So instead of having 2 black holes spiraling and merging together, in this case we had 2 neutron stars, or the cores of dead massive stars, collide. What was extra interesting about this is, since it's 2 objects that are already emitting light, you might expect that we should be able to see a bright flash of light when they ultimately collide and merge together, and that's exactly what astronomers saw with their telescopes. So not only do we have the gravitational wave detection, but we also have light detections at various wavelengths from different telescopes that allow us to pinpoint exactly where and from what galaxy this binary neutron star collision occurred. So I'm going to play you this video. This one's about 4 minutes or so. It's going to describe the detection, show you the galaxy, and give you all of the cool details.
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that, together, collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of 2 neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, a gravitational wave, CHIRP, was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these two fundamentally different types of waves could have come from a single neutron-star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 full moons. Adding information from an independent gamma ray detection from the Integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with the target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect a signal of this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Swope telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes over the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, the neutron-star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of a neutron-star pair before their collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events have played a formative role in shaping the world around us. These results, for the first time, confirm that neutron star mergers create precious elements like gold and platinum, as well as a host of other heavy elements all across the periodic table. Explosions like these, through our cosmic history, have seeded the universe with the materials that later would form new stars, new planets, and beings like ourselves who look up and wonder.
So we're going to jump ahead a little bit now to detection number 19. That's gravitational wave 190521. And this detection was, again, two black holes orbiting around each other, spiraling in and ultimately merging. But what was particularly exciting about this collision is that the two black holes were the most massive black holes we've seen collide and produce gravitational waves to date. One was about 85 solar masses and the other was about 66 solar masses. So you can see an artistic impression of what it might look like as these two black holes collided and were surrounded by light from gas and dust and stars around them. And on the left-hand side, we can play a little simulation of the mergers here. There we go, we can get it started. So the two circles are the two black holes, and the simulation zooms out so that you can actually see the waves. As the black holes get closer, the waves get stronger, they ultimately combine, and we get that ring down, and the gravitational waves, ultimately disappear. Now, this is what we've seen in other black holes, except because these two are so massive, when they combine together, they create a black hole that's around 140 solar masses. And that is a very rare type of black hole we call an intermediate mass black hole. In short, we know how to create, or I should say, we observe two different types of black holes. Stellar mass black holes that are created at the end of a massive star's life. They are 100 solar masses individually or less. And we have supermassive black holes that can be hundreds of thousands to millions of times the mass of the sun. But anything in between, we have not really seen this kind of intermediate mass from like 100 solar masses up to maybe 10,000 solar masses. We have not seen a lot of black holes in this mass range, and we're not really sure if or how they would form in outer space. But black holes colliding and merging is definitely one possibility. And in this case, we do believe that we detected the creation of an intermediate mass black hole. So this was a neat discovery. It kind of opens our eyes to how black holes of interesting masses are created. And it also might lead to, how we ultimately create a supermassive black hole, because that's still a bit of mystery as well. Are supermassive black holes created from just a ton of material that collapses relatively instantaneously? Or is it a bunch of smaller black holes over time that ultimately build up and create these massive objects we see at the center of galaxies? We just don't know. But maybe gravitational waves will help us figure that out. The last detections that I want to cover in detail are detections number 21 and 22. These are both detections of a binary black hole neutron star merger. So in each case, you had one of each. You had a black hole and a neutron star. They were orbiting around one another. They ultimately spiraled in, collided, and the black hole consumed the neutron star. You can see the mass ratios on the left-hand side. In both cases, the black hole was more massive than the neutron star. So in 21, you had a 9 solar mass black hole and about a 2 solar mass neutron star. Number 22 was a 6 solar mass black hole and a 1.5 solar mass neutron star. If we watch the little video on the right, we can see a simulation here of what's actually happening. So the blue is representing the gravitational waves emanating from the system. And in the center there, it's going to zoom in. You'll see the black hole, the gray circle. The neutron star is represented by the orange circle. And as they spiral in towards one another, ultimately the neutron star will fall into the black hole. You'll see a burst of gravitational waves, and then everything kind of settles down after the collision. So with this, we had one object where we don't see any light, the black hole. We had another object, a neutron star, that does emit light. So you might expect that in this case, we should also see a flash of light with our telescopes corresponding to when the two objects collided. Well, it turns out that wasn't the case. So as we just said, we would expect, a neutron star glowing brightly that's approaching a black hole to emit light. And as the neutron star gets closer to the black hole, it's going to get unstable. Basically, the gravitational forces from the black hole should tear the neutron star apart. That's what you're seeing in the animation here. There's a black hole that's grabbing onto some stellar material. You can see that it whips it around in a circle, it tears it apart, and the light then travels out into outer space. So we would have expected to see a flash of light from these two collisions, but no light was seen. So what does that mean? Well, it doesn't mean that our theories are wrong. What it likely means is that the black hole just ate the neutron star in one bite. So instead of this kind of being a slightly slower dance where the neutron star was ripped apart, the neutron star likely fell into the black hole almost instantly and didn't emit any flashes of light in the process. This is expected with the black hole mass and neutron star mass difference that we saw in the previous slide. Scientists kind of expected this to happen, but interesting to see it in action, right? Basic theory says black holes should tear things apart right before they fall in, but in this case, the mass differences allow the neutron star to just get gobbled up right away with no additional light to be seen. So another great example of a cool gravitational wave detection. So to wrap things up here, I want to show you a very classic graph that you often see released with a lot of the press releases for gravitational waves. These are the masses in the stellar graveyard, or basically a chart that shows the two objects orbiting one another, their masses, and what they combine into, or how massive an object they create. So basically, either yellow or blue. The yellow are neutron star collisions. The blues are black hole collisions. Let's just take this case as an example here. We have what looks to be a 6 or 7 solar mass black hole combined with, say, an 11 solar mass black hole, and that produces something like a 17 or 18 solar mass black hole in the end. So you can see how these more massive objects are created as either neutron stars or black holes in spiral and combine together. And this chart shows all 90 gravitational wave sources detected as of the last big data release, which was November of 2021. So this kind of shows you that most of the detections were binary black holes. We do have some neutron star pairs and also a couple of binary black hole neutron star mergers that ultimately created a slightly more massive black hole in the process. So why should we care, right? Why did I bother to make a talk like this? Why should you care about anything I've said for the last hour? Well, gravitational waves are a really important scientific way for us to study the universe. First of all, they are a direct test of general relativity. Anytime we can do an observational test and actually prove that some of Einstein's mathematical work is correct, that's phenomenal, right? Because Einstein's theories, they're a bit out there. But so far, every test we've done has shown to be pretty accurate. So as crazy as relativity can be, that does seem to be the best way to describe all of the physical processes in our universe. Gravitational waves also let us observe properties of objects that don't emit light. So we would not have any other way of detecting or studying these black hole pairs in particular because they don't emit light. So our regular telescopes are no good. And finally, one thing that we hope to do in the future, not quite yet with technology that we have, but in the future, we may be able to detect gravitational waves that occurred shortly after the Big Bang, shortly after the universe is created. If you look at my little chart down here, we've got the Big Bang, the universe expanded and inflated and has continued to grow in size ever since. Light was officially emitted by the universe about 380,000 years after the Big Bang, so regular telescopes only allow us to see out this far. Anything prior to that is not visible with a standard telescope because light was not released in the universe yet. But we think gravitational waves were emitted at a point called inflation, when the universe literally inflated in size very quickly. And if we can detect these gravitational waves, which by the way occurred 10 to the minus 32 seconds, or this tiny fraction of a second after the Big Bang, then we might be able to better understand what happened in the Big Bang, how our universe got so big, and why it is currently continuing to expand and grow in size as we speak. So gravitational waves are going to really open up our eyes to a lot of different ways to study other unique objects. And the more we improve our technology, the more gravitational wave detectors we build, the better off we will be in understanding our universe. In the last minute that I have here, I just want to quickly mention what's coming up next. So we have gravitational wave observatories on the ground. Why not put one in space? So there has been a proposal for LISA, the Laser Interferometer Space Antenna. Same idea, shoot lasers down long tubes, or in space you don't really need tubes, you just shoot the lasers. And you basically make this giant triangle in space where the length of the arms, the lasers here, they can be as long as 2.5 million kilometers in distance. The longer your baseline, the longer your arms, the more sensitive you are to faint gravitational waves. So it's a device like this that will allow us to hopefully detect gravitational waves from the beginning of the universe someday. So I'll wrap it up here. Lisa will hopefully launch in the late 2030s. 2037 is the current date. But I can't wait to see what other gravitational waves we detect. And especially once Lisa goes up, I think we'll have a much better standing of the very beginning of our universe.